Hello, welcome to the course Electronic System Design. In the last lecture we discussed about the resistance color codes and we saw that there are two types of components, the passive components. One is the through hole components for which we have to dig the hole in the PCB and mount them. The other type of components were the SMD components or the surface mount devices, where we need not to put the hole in the substrate, we just need to put some pads, specifically designed pads on the PCB, and we need to put the device on top of these pads and we heat up the whole assembly and automatically the connection will be made. So, we saw only the resistance, capacitance and inductance in the last lecture. These are passive components we use for making the circuits. However, to make a complete circuit or a complete electronic system, we need some other component as well apart from R, L and C. For example, we need diodes, we need BJTs, MOSFETs, we also need integrated circuits, we use displays, we used the push buttons, and there are so many things we need to make a complete electronic system. So, apart from these R, L and C, we also need these components or these modules. These are also available in PTH form or in SMD form. So, today we are going to discuss what these components are and how these things are made. So, for an electronic system design, so any electronic system, it needs multiple types of components. For example, it may have R, L and C. It may have diodes and transistors. It may have integrated circuits. It may have displays, buttons, etc. So, here we have so many components which combinedly make a electronic system. RLC, these are passive elements. However, these diodes, transistors, integrated circuits, mainly these components, these are made upon the semiconductors. These are semiconductor based devices, and the manufacturing of these devices is quite different than our R, L and C, which are our passive components. So, today we are going to see how these components, these semiconductor devices, how these are made and how these are being used in the electronic systems. So, for example, we have here these RL and C along with other semiconductor devices. And here we see on the left we have a complete system. It can be any electronic system here. So, this electronic system is a schematic which we actually make in the CAD software. We connect all the components together and we simulate this whole schematic, and we check what is the performance of this system, and we design this system in CAD software to meet our end goals or some specifications. So, once this schematic is made and this is as per our expectation, then in the next step we make this on the hardware which is called the PCB. So, here we see this schematic is converted to a complete PCB, which is this green color FR4 substrate. On top of this we have multiple components together. So, we may have here resistors, inductors and capacitors along with these ICs. These are black colored components, these are our ICs, these are all our semiconductor based devices, and these are in the packaged form. It means inside this there are multiple semiconductor based devices. For example, transistors, there are so many transistors inside these ICs, and we may also need some discrete transistors as well. So, this transistor is available in the discrete form where only one switch is available that we can buy and put in the PCB. So, these semiconductor devices are now we have in two forms. One is in the discrete form where only one switch is there, just like one resistance, it is a one transistor, and we may have integrated circuits. We have so many transistors joined together already to perform a certain function. So, if we see for example, if we talk about the Intel microprocessor, Intel's, let us say the 4004 microprocessor, so here we have many devices, so many transistors connected together So, this is the die photograph of a Pentium. This is Intel's microprocessor, which is 4004 processor. Microprocessor. This is the die photograph. And on the top we have this packaged microprocessor. So, here we see the die photograph. Die photograph we can see on the single silicon substrate. There are around 4000 or so MOSFETs, which are transistors. These are joined together to perform a certain function, this microprocessor is able to perform or able to program. We can program this microprocessor to perform a certain function. So, these MOSFETs are already joined together to achieve that performance. This is the photograph. This is actually very small piece of silicon. This is put in a protective package, which is shown here by the packaged microprocessor. We can see here there are so many pins coming out from this package. This is a dip kind of package, dual inline package. So, this is the very old microprocessor which was launched in typically 1971. Then this processor, over the time we have learned how to integrate many MOSFETs together and perform different functions all together. So, initially in 4004 typically around 2000 or 2300 transistors were there joined together. However, nowadays with Intel Pentium microprocessor, there are billions of transistors which are joined together. We can see that in a commercial package, something like this. This is the commercial processor available, and this may have a whole grid of pins. We can see compared to the 4004, which has only 14 pins here, and here in these all these small balls or small circuit, these are all the number of pins. So, we can see there are so many pin count increase compared to the very first microprocessor. However, all these microprocessors and all these ICs, most of the time these are made up of silicon, and on silicon we fabricate a transistor which is something called a MOSFET, or the metal oxide semiconductor field effect transistor. So, all these ICs having a single building block which is a MOSFET, which is joined together in billions of count to perform a certain function that is called the ICs or the processor. So, let us discuss this MOSFET a little bit. So, this MOSFET this is an acronym for metal oxide semiconductor field effect transistor. So, we have this M, O, S, F, E, T. These are the initial 6 letters which we combine together and we call it the MOSFET. So, this MOSFET is the most common type of transistor which we use in IC fabrication, and this MOSFET is typically used for switching or amplifying the signal. So, there are two types of cases where we use MOSFET. One is as a switching device, where this is used as a switch and we are interested in on and off region. The second application is for the amplification, where we are interested in how much gain we can get from this device. So, we are not particularly interested in on and off, but we are interested in the transition region where the MOSFET is turning on, and during turning on how much gain the MOSFET has. So, that is typically for the analog applications, and on off where we are using as a switch, that is used for digital IC design. So, this MOSFET is nothing but a voltage control device where we apply the voltage and we change the transconductance or the capability of driving current. So, that we can change by applying a voltage. This is a 4-terminal device. However, we typically use only three terminals: source, gate and the drain. Fourth terminal is the body, which is typically tied together in form of when we fabricate in terms of ICs. In discrete component, if we buy a single MOSFET from the market, generally this comes up with three terminals: source, gate and drain only. The bulk substrate or the substrate contact, that is internally tied to the source. So this MOSFET is a three terminal device in discrete form, however a four terminal device in ICs or integrated circuits. This is a it has a quite high switching speed, and there are two types of MOSFET. One is the depletion type MOSFET, one is the enhancement type MOSFET, and we have in the same enhancement type we have again N channel devices and a P channel devices. So this is the typically a MOSFET. So let's write these points down. So the first is the MOSFET is the most commonly used field effect transistor. These are used for switching or amplifying electronic signals. These MOSFETs are voltage control devices. MOSFETs are four terminal devices. MOSFETs has very high switching speeds. There are two classes of MOSFETs. One is the enhancement type, and the second is the depletion type. And further in this classification there are two types of each one of this. One is the N-channel MOSFET and the other is P-channel MOSFET. So as we have seen, MOSFET is of two types. One is the depletion type MOSFET and one is the enhancement type MOSFET. The difference is enhancement type MOSFET, there is no channel in the off state. We have to apply the voltage externally to create the channel or to turn on the device. In the normal case, this MOSFET is usually off. So we have to turn it on by applying voltage. However, in the depletion case, there is always a channel exist. It means the device is always on and we have to turn it off by applying external voltage at the gate. So this is the difference between enhancement and depletion type. Further, in the enhancement type, we have two types of MOSFETs, which is N-channel MOSFET and P-channel MOSFET. Typically, we use enhancement type MOSFET because of the power dissipation issue. So in enhancement type MOSFET, we further have P-channel devices where the channel, which is the conductive channel carrying current, this current is caused by the movement of positive charge carrier. So that is called P-channel devices. In the N-channel devices, we have electron as the charge carrier. So this is the difference between P and N-channel MOSFET. And typically we study N-channel MOSFET because of the ease of discussion. So enhancement type MOSFET, and further in enhancement type we want to discuss the N-channel enhancement type MOSFET. So let us discuss this MOSFET in some detail. So first we need to see how a MOSFET look like. So for this we see the cross section of a MOSFET. So if we draw the cartoon of a MOSFET, which is N-channel MOSFET, it looks something like this. We start with a P-type substrate. This is P-type, and in this P-type we have something called a gate. This gate has two portions, one is the oxide layer and one is the contact layer on top, and then we have a source contact and a drain contact. These are made up of N plus region, and we have a body contact as well, which is made up of P plus region. So now we have four terminal. One is the source or S, the other is the gate or G, third is the drain or D, and fourth is the body contact, which is generally represented by B. So this is the MOSFET cross section area where we start with a P-type substrate, which is a silicon semiconductor lightly doped with P-type impurity, and then we have a gate and two contacts, source and the drain. There is a current flowing between source and the drain depending upon the gate voltage, and the fourth terminal is the body terminal. So we have here 4 terminal MOSFET structure. So this is the cartoon roughly what we draw on the paper. However, if we see the MOSFET actually on the silicon, if we take the silicon wafer and cut it perpendicular to this surface, then we see the actual MOSFET structure. This looks something like this. So here you can see this is the gate terminal, this is our source terminal, and this is the drain terminal. So we can see here we have source, gate and a drain. Body terminal is not shown here, and below this gate terminal, this is the region where the current flows from the source to the drain. So this is the channel which is causing the current to flow in the MOSFET. So this is a typical cross section. Now let's see closely how this MOSFET actually works. So let's discuss that in detail. So how this MOSFET actually works? So let's consider this cross section, which is a bit closer cross section to the real MOSFET. Here we have the gate, which is a polysilicon gate. So this is the gate terminal, which is made up of polysilicon, and below this, if we closely see, we have a certain gate oxide region. This is a very thin layer of oxide, which is an insulator, and this is sitting on the p-type substrate here. This is complete silicon substrate which is doped of p-type impurity. It means this region is rich in positive charges, or we call the holes. So this positive charge is everywhere in this p substrate, and on top of this we have source region where this is doped N plus. It means there are electrons everywhere. This region is rich in electrons, which is negatively charged. So if we see closely, this negative charge is here, negative charge is on the drain side and source side. However, there is no path below the gate oxide where this current can flow. So in the normal state where we are not applying any voltage, there is no charge carrier which can flow from source to drain, so there is no current. So initially at zero bias there is no current. At zero bias no current. Between source and the drain, or IDS, source to the drain. However, when we apply a voltage, positive voltage, at the gate, this positive voltage we are applying across this gate oxide. So because of this positive nature, these positive charge carriers will be repelled from this surface, and if the voltage is high enough, it can attract negative charges to this surface. Because of application of this positive voltage, this will attract negative charge very close to this surface, and because of this, now we see these electrons can now move from source to drain. It means if we apply a positive voltage at the gate, there is a channel formation below the gate oxide, and the current will flow from source to drain if we are applying certain voltage between source and the drain. So typically source is 0 volt, and we apply, let's say, 1 volt here, which is a positive voltage. So there is a current flow from source to the drain. If we plot the current versus the voltage I apply between source and the drain, the characteristic look something like this. Let us see the ID versus VDS characteristic of this MOSFET. This is the drain voltage or drain current between source and the drain, and x axis is the voltage, drain to source voltage in volt, and this current is typically in amps or milliamp, and the characteristic look something like this. Initially the current increases because when we increase the voltage, there are so many carriers which will rush from source to drain. However, at certain point, which is called the, let's say, the saturation point, after which there are no more charge carriers in the gate, under the gate, which can come, which can respond to this high VDS. So the current is going to saturate. So this is called the saturation region. Now, if we increase the gate voltage, this is the gate voltage which is causing these charge carriers below the oxide. If we increase this, then the amount of current is going to increase. So, for example, if we have different gate voltage which can cause more charge carriers in the channel, so the current will increase. If we increase the gate voltage furthermore, then the characteristics will be something like this. So there are, for example, VG1, VG2 and VG3. So for example, VGS equal to 1 volt, VGS equal to 2 volt, and this characteristics is VGS equal to 3 volt. So as we keep on increasing the gate voltage, the amount of current increases. This is the typical ID versus VDS characteristic of this MOSFET. So this is called ID VDS characteristic. Similarly, we can draw ID VG characteristic. This y axis same current, but now x axis we have the gate to source voltage in volt. So the ID VG characteristics look something like this. Initially the MOSFET will be on, and if we further increase the gate voltage, there will be a charge formation below oxide and the current will increase. So this voltage is typically called VTH or the threshold voltage. This is very important voltage for a MOSFET. So this is how this MOSFET actually works, and we have this threshold voltage which we can measure using ID versus VGS graph, where the channel forms or the current sharply turns on, current increases. That point is that voltage which we apply at the gate is called the threshold voltage. So below this threshold voltage the device is off, and above the threshold voltage we generally consider the device is on. So this is our ID versus VDS and ID versus VGS characteristic. So this is how a MOSFET works. Let's see some equation for a MOSFET which we generally use. So to represent the MOSFET characteristic, we have the MOSFET current equation, which is ID or IDS. This is given by half mu n, which is the mobility of charge carriers. C oxide is the gate oxide capacitance. Then W upon L, where W is the width of transistor and L is the length of transistor. In the bracket we have VGS, which is the gate to source voltage, what we apply on the MOSFET, minus VTH, or the threshold voltage, which we just measure from IDVGA graph, and this is whole square. So this is the characteristic equation for a MOSFET. From this we are multiple time interested in calculating the GM, which is called the transconductance of MOSFET. This is nothing but del ID over del VGS. We just differentiate the above equation with respect to VGS and it comes out to be mu n C ox W by L VGS minus VT. And there are other expressions as well for this MOSFET equation. Now if we see the symbol which we use to represent MOSFETs, so there are multiple symbols. For example, for a NMOS we have this is the symbol for an NMOS, and this is the symbol for a PMOS. This is the symbol generally we use for digital design, where this gate without any NOT represent NMOS and NOT at the gate, it represents that the logic is inverted, and we use this symbol for typically for digital designs. For analog design, however, we use these symbols for NMOS and PMOS, though both are same thing. For NMOS we denote the flow of current at the source junction. This is the symbol for NMOS, and for PMOS this is the symbol of current at the source terminal. This is the symbol for PMOS. So these are the symbols for NMOS and PMOS, though both are same, but generally one type of symbols we use for digital design, one for the analog design. These are the symbols which we use to make schematic, however they do not have any physical significance, or it's not like the MOSFET looks something like this. These are just the symbolic representation of a MOSFET. These are 3 terminal symbols. However, if we want to have a 4 terminal symbol, then we can have a body terminal something like this and something like this. So this is the 4th terminal. However, most of the time we do not use the body terminal to bias this MOSFET. Typically it's not available. So we use 3 terminal symbol or the 4 terminal symbol. So as I said, 3 terminal symbols are more frequent because in the discrete semiconductor, discrete components, this comes up with only 3 terminal component, which looks something like this photograph here. So here we have this MOSFET, which is a commercially available MOSFET, and it has 3 terminals. We can see here, this is one gate terminal, drain terminal and the source terminal. So this has only 3 terminals now. So this is the MOSFET device which is generally available in the market, which we can buy from any online vendor or so. So this has 3 terminals. This is a PTH type of MOSFET where we need to dig 3 holes and put this MOSFET on the PCB, solder it, and it acts like a transistor. So, the first one is the MOSFET, which is most of the time used, almost 95% of the ICs made up of MOSFET as a device. However, certain times or in older times, and there are certain application even nowadays also where we cannot use the MOSFET devices and we have to use something called a BJT or the bipolar junction transistor. That is also a transistor very different from the MOSFET. These BJTs are still in use for certain applications where the MOSFET cannot work. So, these BJTs are very much different compared to the MOSFET, how the MOSFET works. The entire working principle of BJT is very different than a MOSFET. So, let us discuss briefly how a BJT look like and how the BJT actually works. So, we can write BJT which is an acronym for bipolar junction transistor. Okay, here. So, this is an acronym for bipolar junction transistor. Here we have these key terms. The first one is, let us say, the bipolar. So, this first term says there are two types of charges which are having different polarities. There are two polarity charges which are there to make the conduction possible. So, here we have holes and electrons. These are determining the characteristic of transistor. Second one is the junction. So, we have semiconductor junctions which are forming this device. So, we have semiconductor junctions. Which made up this device, we will see in the next few slides. And then the third word is the transistor. It means that there are three terminal devices where one terminal, the third terminal, controls the current between the two terminals. It means there is amplification or switching possible through third terminal. So there is a amplification and switching possible in the device, which is controlled by the third terminal, which in this case, or the bipolar junction transistor, we call base. So in MOSFET we have three terminals, which are source, gate and the drain. However, in the BJT case we call these three terminals as emitter, base and collector. So let us see the BJT and how it works in some detail. So BJT, or the bipolar junction transistor, there is a junction transistor consists of silicon crystal, which is sandwiched between two p types. So there is a n type silicon sandwiched between two p type There are types of transistor which are NPN and PNP. One is the NPN and the other one is PNP. These are two different type of transistors, and there are three regions or the three portions of transistors. One is the base, one is the emitter, third one is the collector. And in bipolar, means both electrons and holes contribute to current flow. So these are some of the characteristics of BJT. We have N-type region, which is the base region, and this is sandwiched between two P-type regions. So we have P, N, P. There are three regions in the transistor. There are two types of transistor, where one we can have P and P and the other one we can have N, P, N. There are two types of transistor, and we have these three regions named as emitter, base and the collector. And unlike the MOSFET, we have electrons and holes, both of the charges, which contribute to the current conduction. So let us see the working of the BJT in little detail. So, we have a BJT So, typically a BJT something look like this. We have P region, we have N region, and we have again a P region. Then we bias this device in such a way, the first two terminal, which is, let us say, the first terminal is called emitter here. So, this is emitter junction and this is our base junction. So, this junction, emitter and base junction, is forward biased. So, here we apply the voltage such a way emitter base junction is forward biased, and the second biasing, which is between base and the collector junction here, this junction is reverse biased. So, here we use VCC in such a way, this junction is reverse biased. So, when we have this emitter and base junction forward biased, it means there will be a current flow just like a normal diode. So, we see by this magnitude of this arrow, there is so many charge carriers which are flowing from this emitter to the base. However, this width of the base is very small. If we can see from this diagram, compared to emitter and collector, this width of base is very small, and the doping of this base is also very small, so that not many carriers which are coming from emitter, they cannot be absorbed in the base region. So, what they will do, they will pass from base to the collector. So, most of these electron or holes, they will go from base to the collector, and this junction is reverse bias. So, because of this reverse bias, this can offer a very high transconductance. However, there is small amount of charges which can recombine in the base itself, which can cause a small amount of current, which is called IB, or the base current, and the majority of current is the emitter and collector currents. These are the majority current, and small amount of current can flow in the base. So, this is how a BJT works. Let us write it down in some points. So, the first one is emitter base junction is forward biased and collector base junction is reverse biased. Base region is very thin and lightly doped. Base current is very small. And if we see the KCL, we can write the emitter current is equal to the collector current plus the base current. Emitter is the one which is supplying all the current So, majority of this emitter current goes into the collector, and some portion of this current contributes the base current, which is the controlling current. If we increase the base current, the amount of current from emitter to collector that increases, and that gives us the transconductance in this device. So, this is how the BJT actually works. So, the operation of MOSFET and BJT, however, there are separate courses which we study to know the exact operation of BJT and MOSFET. Here we discussed only very small, very briefly how the MOSFET and BJT works, and now let us see how this BJT actually comes from the market if we want to buy this. So, these are the typical packages which are available in the market. So, these are BJTs, commercially available packages. So, BJT again, it comes in different types of packages. For example, the first one is the PTH form, where we have 3 pins coming out of this component. We have to dig the hole in the PCB to mount this BJT on the PCB. The second one is this SMD type of package, where these pins need not to put the hole. We have to make the pattern of pad on the PCB, put the SMD device on top, and we heat it up. That pad will stick to all these pins. So, that is SMD type, and we can have, even for power application, we can have different types of BJT packages. So, today we discussed the MOSFET, which is mostly used as a switch in all our ICs and discrete components as an active device, and BJT. There are some circuits which require the use of BJT, cannot do the same function with a MOSFET. So, only in very limited cases we use BJT structures as well in our electronic system design. So, that is all for today. Thank you.